Hello and welcome to GCSE Quantitative Chemistry with Mrs. Castanera. We're on Lesson 6, Calculations, Solutes, Solvents and Solutions, which is a higher tier lesson from the higher tier booklet. Today's keywords are solute, solvent, solution, concentration, mole, mass and volume. You'll need your highlighter to highlight these, and by the end of the lesson you should know what all of these words mean and how to use them. Many of them we have used before. We have here the list of content from the specification. So we're going to start by completing the knowledge check. We're on page 30. There are 8 questions, so pause the video whilst you attempt those questions, please. So let's review those questions. Make sure you're using a pen in a different colour to the colour that you used to write your answers. Question 1, define the law of conservation of mass. Well, the mass of the reactant should always equal the mass of the products. Question 2, define limiting reactant. So that's the idea that the reactant is used up first. So the limiting reactant is the reactant that gets used up first. Question 3, define excess. So the reactant that does not get used up as there is more than required. So the idea that there's more than enough of it for the reaction. There's excessive amounts, spare amounts. Define MR, well that's the relative molecular mass, and to calculate that you can add up the AR, the relative atomic mass, of all the atoms in the compound. Question 5, state the value of a mole. Well that is 6.02 times 10 to the 23, and usually we're talking about atoms. Question 6, give the units for measuring mass. So that's grams or lowercase g. Question 7, give 2 units for measuring concentration. Okay, so there are several answers available for this. So grams per decimeter cubed, grams per centimeter cubed, or moles per decimeter cubed, or moles per centimeter cubed. So there are 4 to choose from. Any 2 of those will get you a mark. Question 8, give the units for measuring the amount of the substance, whether that's moles or mole. So give yourself a mark out of 8 for this. So today we are going to be explaining how the mass of a solute and the volume of a solution is related to the concentration of the solution. We are also going to be able to calculate the mass of a solute in a given volume of solution of known concentration in terms of mass per given volume of solution. Terminology. Solvents are usually liquids that a solute, typically a solid, is dissolved into and then form a solution when they're mixed. If we alter either the solute or the solvent, we can alter the concentration of the solution by changing the amount of solute or solvent. The mass of a substance is measured in grams, the amount in moles. That's a substance. Volumes of solvents are measured in either centimetre cubed for small volumes or decimetre cubed for large volumes. This is all familiar content that we've done in previous lessons. Changing concentration. Changing the concentration of a solution can alter the rate of a chemical reaction. That's how fast the chemical reaction is occurring. More concentrated solutions will have atoms or molecules that are closer together, so there is a greater probability of successful collisions, and so that gives us a higher reaction rate compared to a solution with lower concentrations where the atoms or molecules are more spread out, and this has a lower chance of successful collisions. So let's summarise that. So first of all, change in concentration can alter the rate of chemical reaction. More concentrated solutions will have greater probability of successful collisions because their atoms or molecules are closer together, and so that means we have a higher reaction rate. However, at low concentrations, their atoms are more spread out and we have a lower chance of successful collisions. Okay, so we'll use a different colour. So for lower concentrations, okay, the atoms and molecules are more spread out and there is a lower chance of successful collisions, which leads us to a lower reaction rate. Okay, I'm going to highlight that part. So I've done it in 2 separate colours to show the 2 opposites that are occurring there. So to increase or decrease the concentration, we've done this before, we've talked about this before in terms of squash in particular. So we can alter the volume of the solvent, so for squash that's water, or the mass or amount of the solute, that would be the squash itself. So we don't actually use the word stronger or weaker when describing concentration, even though we do use those terms for squash, okay, because they mean something completely different. So we must talk about our solutions in terms of concentration. High concentration, not strong, and low concentration, not weak. Okay, so the concentration taboo, talking about terms strong and weak. Okay, so the terms strong or weak in chemistry refer to the ability of a chemical to do something. Okay, so strong and weak is talking about the ability of a chemical to do something. And normally we use this when we talk about acids and alkalis. So a strong acid is more able to form an acidic solution or an alkali solution better than a weak acid. Okay, so we'll talk about this in a later unit, but as a general rule, don't mention the word strong or weak when talking about concentration. Instead, talk about concentrated or dilute or high concentration and low concentration. But we're going to add that part in. So it's concentrated or high concentration. So or high concentration or low concentration. Okay, so those are the alternatives, high concentration, low concentration, instead of concentrated and dilute. Okay, so there's now an activity here that we can't do, unfortunately, as it's a practical. So we're going to move on until we get to page 32. So unfortunately we can't answer any of these analysis or conclusion questions because they're around the practical. However, we have been given a set of results here for this practical, okay? So this is a practical where the reaction occurred more slowly or more quickly at different concentrations. So it shows the concentrations here. So remember we're talking similar to concentrations of squash, so with more or less of their solvent or solute in them. And depending on the concentration, this affects how long it took the colour to appear or the colour change to occur in the chemical reaction. Okay, so this is similar to the experiment that would have been performed. Now, as you can see, okay, there is 3 trials and an average. Now, the average must be calculated. So, have a look at the results and use them to calculate the average in this column, please. I recommend using a calculator for this, as that's always allowed in science. So pause the video whilst you calculate the average of these 3 values. So to remember, to calculate the average, you add up the values together and then divide it by the number of values there is. So in this one, you would do 60.8 added to 63.6 added to 62.4. That would give you a value, a total number. And then you would divide that number by 3 because there are 3 different values, and that would give you the average time that it took for the colour to appear at 0.1 concentration, or 0.1 moles per decameter cubed. And you will write that in there. So pause the video whilst you do that, and then we'll mark them together. Okay, so here we have our results. So the average for the first one was 62.2, then it was 32.3, 17.3, 8.0 and 2.3. Now you may have noticed that I've highlighted this value here because there's something a bit off about this value. And you'll notice that in trial 1 at 0.4 moles per decameter cubed concentration, it only took 16 seconds, and trial 3 took 16.5 seconds, 16.5. But this trial here took 19.3, which is a lot longer than the other 2. In fact, this is the odd one out. This is what we call an anomalous result. So this is an anomalous result. Now, what do we do with anomalous results? Well, we disregard them. That means that we ignore them. So if you've written 17.3, that's absolutely fine, and I've given you the mark for that. However, the best thing to have done with that would actually be to add up the 16 with 16.5, ignoring 19.3, and then divide it by 2, because you only use the 2 values, which would give you 16.25, which we round to 16.3. And so our result for this one would actually be 16.3. And if you've written 16.3 as your answer, that is also accepted and correct. In fact, it's more correct than 17.3, but either is acceptable at this point. So the next task is on page 33, where you need to use the values we've just done. So you need to use the values we've just calculated to draw a graph. Now it says calculate the average time, which we've done, and plot the average time against the concentration on the graph below. Okay, so this is the time taken here, this is the concentration here, and you need to choose a suitable scale. If you're not sure about the scale, I will go through that next, okay, but at the beginning of the answer section. Okay, so if you're not sure about scale, you can stay with me and we'll explain that. So draw a graph of the average time against concentration. Pause the video now if you're confident you can do that. So if you're not confident about that, that's absolutely fine. And I highly recommend doing the following for scale. So I've worked this out by counting the number of squares, and there are actually 20 squares in each direction here. And I know that my data, we'll start with concentration on the bottom. So my data of concentration goes from 0.1 to 1.6. Now I have 20 squares. So for me, I think a good way of doing this is if I round this up to about 2, if I say 2 is the total amount. So if I take my calculator and do 2 divided by 20 squares, okay, each square becomes 0.1. So 2 divided by 20 gives you 0.1. And so each square will become worth 0.1. So I've just drawn a basic line here, basic scale, okay, and I've marked evenly points along it. Now each of these points is every 2 squares. Now I could do them every 1 square, that would be absolutely fine, okay, and that's absolutely fine for you to do. Now you'll notice that I said each square was going to be worth 0.1, so this is 0, this is 0.1, and I'm going to zoom in so you can see this a bit better. And so this one will be 0.2 and 0.3 and 0.4. Now you'll see these are a bit close together. So I'm going to continue the rest of this scale, just marking every 2 squares, like so. So you can see it's a bit clearer as to what's happening now. 1.2, 1.4, etc. All the way up to 2.0. Now, I only need to go up to 1.6, but I'm happy because that fits within my scale. Okay, so the same idea applies in the vertical scale. Now this time, the time goes between 2.2 as our smallest number and 62.4 as our largest number. So we need 60 to fit within here. Now again, there are 20 squares. Now, this is a little trickier, okay, because it's going to be hard to divide this one up. So what I recommend for this one is you could work it out by going up in 5s or 10s. So 10, 20, 30, 40, 50, 60. Well, that's not going to take up very much space if each square is worth 10. So what if each square were worth 5? Well, let's try that. That might make it a bit bigger. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. Well, it needs to go to at least 65 because it's 62.5. So that takes up more than half of my scale. So I think that's a very good scale to use. So let's do that. So as you can see, once again, I have done just a simple scale on the axis as we go up. So as we said, each one's going to be worth 5. So this is going to be 0, and then 5, 10, 15, 20, 25, 30. And it's looking quite crowded here. So I'm going to continue my scale like in 10s rather than 5s, doing it every 2 squares. And we only really need to go to 65, which is here. So I've stopped my scale here. You could, if you wanted to, do some more here up to 90 and so on. So that's not a problem, but we're only going to be using up to about 65. So now you have a sensible scale. You can draw these either doing every single number or by doing it every other square, which is a bit clearer, I think. And so now you have a go at plotting these scales yourself, please, and then try plotting your results on there. So pause the video to do that now if you haven't yet done that. So if you're not sure about how to plot results, we're going to do a brief just overview of how to do that. So you'll need to have the data in front of you to do this. So for 0.1 concentration, the average was 62.2. So let's do that. So 0.1 concentration, that's this number here, this value just here. So we're going to follow all the way up, and you can use a pencil if you wish. I highly recommend using a pencil so you can rub it out. Now my pencil doesn't show up very clearly. So you go up this line here at 0.1. You don't have to use a pencil to do that or a ruler, but I like to use it, especially because it's helpful. Then it was 62.2. So 60 is here, okay. So 60 is there. We're going to zoom in so we can see that more clearly. Now, this is going to be 65. So 62.2 is going to be around about halfway between these two values. So making sure that I'm following the line that I've drawn here, I'm going to put it just here as my point. Now, you can hardly see that probably. So I have gone over it. Once I'm happy with it and I've checked them all, I would then go over it, and you can use the colour or you can use pen like so. Once you're happy with them and you've checked them. I think it's always good to draw lines in pencil and then to go over them later. So it's always good to draw them as crosses, okay, because then at the centre of the cross it's a very clear, precise position. Now if I were to do this point as a circle, that is not very clear. Okay, it doesn't help me know exactly where it is. That's a big range of uncertainty, which is why we use crosses. So pause the video now if you now know what you're doing. If you've already done all that and you've plotted all your points, then please continue watching. So here is the graph I drew. It's not perfect, and I'll explain why in a minute. So as you can see, I've plotted all of my points, so check that your points are in the same positions. Now you'll notice here that it looks like it's a bit messy. That's because I've drawn a red mark, an X for red, for the value 17.3, which would be your answer for the average if you had included 19.3 for the anomalous result. However, the green one slightly below it is the mark for the correct or edited average when you discounted the anomalous result. So they're very close together anyway, so it shouldn't make a big difference. And you should have your points plotted at 0.1, 0.2, 0.4, 0.8, and 1.6, and they must get further apart from each other as shown here. Okay. Now, what I have done here is I did it in pencil first, then drew over it in pen. Is I have done a curve of best fit to show roughly where other values would lie, so you could use this to then interpret what you think the result would be at other concentrations. So say for example, if I had a concentration of, let's say 0.3, what would be the rough time, or what do we reckon would be a good guess for the time it would take? So I would go up until I hit my line at 0.3, so that's the concentration up to here. So it would be about 21, 22 maybe, because that's where it hits, and I'd go across to there. So there's some problems with my line here. As you can see here, it's two lines in fact. So this is something you want to avoid. Examiners will mark you down for this. So you want to be drawing a single clear line as such, not like this section here. And the reason this ended up happening was because the first line I drew wobbled upwards a bit and it wasn't very good. But it is important that you drew this in pencil first, and in your exams you can do it in pencil, and your examiner isn't going to worry about that. They're going to be very happy with that. I simply drew over mine in pen so that it was clearer for the video. Okay, so let's go through the questions. So once you've done the graph, there are some questions beneath the graph. So it says on the table, circle the anomalous result in the data set. Well, we have already done that. It was 19.3. We circled it already. But hopefully you've identified what that was. So if you could pause the video whilst you answer the remaining questions, please. Okay, so let's go through those. So we've already marked this one as correct. Question 2, explain what should be done with this anomalous result. Well, we should ignore it or discount it. Question 3, suggest how the student could improve the accuracy of the time measurement. Well, you may have made some different suggestions, but generally using a digital colour change recorder would be a good idea because it's more accurate accurate and more reliable than the human eye. You may not have known about this being an option, and if we'd have done the practical, we'd have talked about this. Basically, anything that's more accurate than the human eye, or any way to improve it to make it more accurate. Sometimes people would put a cross underneath the colour change so that they could measure it as soon as the cross disappears and the colour is so strong that you can no longer see the cross. Sometimes that's used. It's very difficult to do that though, unless it's a kind of mixture that goes cloudy. For a colour change, that can be tricky. So this is what we tend to talk about using, digital colour change recorders. Question 4, state the concentration that had the greatest precision, the one with the results closest together. So that was 1.6 decameter cubes. The one with the highest concentration, because the results were the shortest and they were the closest together. Okay, so give yourself a mark out of 4 for those, please. Then we're going to move on to the knowledge and application check on page 34. Okay, so there are 13 questions. If you could attempt the questions, pause the video whilst you do so, and then we'll mark them together. Okay, so let's go through those. Question 1. Give 2 possible units for measuring volume. Well, we should know these by now. It's centimetres cubed and decameters cubed. Question 2. Give the units for measuring the amount of a substance. Well, that's moles, or mole is the short version. Give the units for measuring mass. That's grams, or G, lowercase. So precision is how close together repeated results are. So the closer together the results are, the more similar they are, then the higher the precision. If the results are more farther apart from each other or quite different, then they are low precision. Question 5. Give the name for an odd result in data. So we're talking about an anomaly or an anomalous result. Question 6. Complete. Solute plus solvent equals solution. Question 7. Complete. Adding water to a solution will make it more dilute. Question 8. Adding more solute to a solution will make it more concentrated. Question 9. Calculate the concentration of 120 grams of magnesium sulfate in 500 centimetre cubed of water. Give your answer in grams per decameter cubed. So because of the difference in units, first of all, you must convert from centimetres cubed to decameters cubed. So you divide 500 by 1,000, giving you 0.5 as your answer in decameter cubed. The second mark is to do the result, which is 240 grams per decameter cubed. Now, if you haven't done this calculation here for the volume, then if you've done 120 divided by 0.5, you can have that for your first mark. So this one is out of 2. Question 10. Calculate the concentration of a salt solution that contained 2 mole of sodium chloride in 2,000 centimetres cubed of water. Give your answer in grams per decameter cubed. So again, the first mark is for the conversion from centimetres cubed to decameters cubed. So 2,000 divided by 1,000 gives you 2 decameters cubed. Again, if you didn't do that first calculation, but you did do 2 divided by 2, that can be your mark for the first one. You can have that mark instead. 1 mark so far. And then your answer would be 1 mole per decameter cubed, so we'll mark for the 1. So that's out of 2 as well. Question 11. Explain how manufacturers of orange and blackcurrant squash are able to make double concentrate solutions to sell in the shops. Well, they simply add more solute to the solution or less solvent. Either of these is an acceptable answer. So less solvent, that'll be less water, or more solute, which is the concentrated squash, to the solution. Question 12. Explain how a chemist could use concentration to slow down the rate of reaction. Well, using a lower concentration of reactants would slow the rate of reaction. There's simply less of them and they're further apart. Question 13. Hyponatremia is a condition where the salt levels in the body become dangerously low and ultimately makes the blood dilute or more dilute. Suggest why long-distance runners are advised to take isotonic drinks that contain salt during a long and arduous race. Well, the reason for that is they need to replace these salts that they're sweating away. So if they replace the salts, that's going to stop them getting hyponatremia. So you need to be talking about the replacing the salts. That's the key phrase, replacing the salts. Okay, and that's just out of 1. So give yourself a mark, please. And that would be out of 15, because there was 2 marks each for questions 9 and 10. If you got 10 or more, that's really good, well done. If you got 7 or less, then you'd need to have another go at that and review the lesson some more, because that indicates you've got a few errors there and there's a few things you really haven't understood. Okay, and that's the end of our lesson. If you have any questions, feel free to email your teachers and we'd be more than happy to help.